then. And you see my screen correctly, right? I have Notepad open. I hope that the stream is showing out well. Okay, so we have the thing we're going to look at today is using vertex array instances and vertex buffer objects and how to draw a lot of the same geometry in multiple different positions at the same time in just a single draw call. So the simple example for this is what you see here is this highlight geos widget, which all it does, it takes each geovent on the map and places this line here that's got this little animation going on. The advantage of this technique is that you can go ahead and draw pretty much as much geometry as you want in an instanced manner, and you can make sure that it's as fast as possible and it's just a single draw call. So let's take a look at a couple of things that enable us to do this. So the reason why we use this is to avoid using gl.Vertex and gl begin end and call and display lists, which are old and cause a lot of performance overhead. So let's take a look at a couple of tools that allow us to do this. So one of them is the Lua shader.lua, which is a wrapper over just shaders in general and allows you to compile them easily, allows you to use them easily, and it gives you access to a couple of things like uniforms, and especially it gives you a good access to the engine uniform buffers. Now IvanD has gone to great length to include a lot of very useful uniforms inside that are accessible for every shader, from things like the individual screen and camera projection and view matrices, to the shadow view matrices, to the illumination of the map, to even a time info. So you have the game frame, game seconds, the draw frame. You have the view and the map geometry available in a uniform parameter buffer, meaning that you waste no overhead in having to set these uniforms every frame when you draw something. You even have a random vector, and you have some very nice things like you have the mouse screen's position and the mouse status and the mouse world position, wind information, team color, and a couple of convenience functions that just rotation and scaling matrices that are useful in GLSL. So if you're not familiar with vertex array objects and vertex buffer objects, my terminology might not be completely correct, but they are basically vertex array objects are a way of taking a vertex buffer object, which is a vertex buffer object is just a set of vertices, and with a vertex array objects, you can wrap an instance buffer around this. So for every element of the instance buffer, you're going to be drawing the entire vertex buffer once, and you're going to be passing all of those parameters to it. Now, because there's a little bit of overhead in updating these individual vertex instance objects, so I made a set of convenience functions. I call them the instance VBO. So basically, whenever you have, like, you want to draw a circle and you want to draw it in multiple different areas, in this case, we want to draw a line in a lot of different areas. That means the same geometry of the line, which is just two vertices, that has to be instanced multiple times. Now, there's an easy way of handling this instancing in a buffer. So there's this instance VBO table is a wrapper around an instance buffer object, and it allows you to very efficiently use it as a Lua table. So whenever you want a new instance, you just push to this buffer. Whenever you want to remove one, you can pop from this buffer, and you can update the existing elements inside of the buffer with the lowest possible amount of overhead because it's keyed with a Lua table. So whenever you add an element to this buffer, then you can also supply an optional key to the object. So it's a standard Lua table, so you can assign a key, so that makes updating and getting elements from this buffer very easy and very quick. I know the implementation isn't the nicest thing in the world, but it works very well and it's extremely performant. And just being able to pop and push into this buffer is very easy because what you're doing generally when you draw, the actual draw call is very little. The actual draw call is we activate the shader that we're looking at. Then we're using draw arrays. Now the draw arrays takes a couple of arguments. First off, you have to define how you want to what kind of elements your vertex buffer contains. Now in this case, it contains lines, it can contain triangles, triangle fans, points, anything you want. And then you have to specify the number of vertices that you want to draw from your vertex buffer. Then you specify, oh, this is optional, this can be nil at this point. And then you can specify a start offset. Now this is the start offset, right? This is the start offset and an end offset into your instance buffer. Because we're allocating a larger instance buffer, and by the way, these tables completely transparently handle resizing the buffer if it grows too large, so you have nothing to worry about there. You can draw as many as you wish, and the way it's set up is that you always draw, whenever you push pop into a buffer, it manages it. So if you pop from it, then it removes that element and copies the last element to its place. So you always have a contiguous buffer of stuff you want to use. It's very useful in that case. So it has a couple of functions. You start off, there's a constructor for it, which is a make instance VBO table. And you specify the layout. Now I'll talk about layout in a moment, the number of elements, and you give it just a name, and the name is only used for debugging. And then it will return you this instance table, which contains the step sizes, the pointers. This is indexed into two different directions. So you have an instance ID, which was the key in the Lua table, to the actual position in the array, and you have the other way around. So where any instance ID is located at any given position. So this is just a two-way table of indexing it. You can clear the entire table. You can make a vertex array object and attach this buffer to, and attach a vertex buffer to this instance VBO. You can resize the whole thing. Obviously, you can push an element into it. Now, this push takes a couple of arguments. Most of them are optional. You have the instance table you wish to push into. You have the instance that you want to push into, which is going to be a Lua array. We're always going to be using Lua arrays in this case, which means that the keys have to be integers incrementing from 1 to the how many elements you have. The instance ID is the optional key that you wish to use. If you don't pass a key, then it's just going to be the index of the element. So that's going to be your key. And then you can choose whether to update the existing element. So you can choose whether that if you want to push in and you're specifying the same key, then you can specify that you want to update an existing element inside of it and not allocate a new one for it, which is very useful. And also you can specify no upload, so you don't upload the entire VBO when this is done. Well, actually, it's done smartly because you don't even upload the entire thing. You only upload the changes into the buffer. But still, if you're going to be updating every element in a buffer, then you want to call it with no upload. And then once you're done with that, you just call the function upload all elements, which is going to upload all the used elements very efficiently. Same with pop. Pop element removes something from the buffer based on the key. If you don't specify a key, it removes the last one. If you specify the last one, then it's just going to decrement the number of used elements inside of the array. And if you specify an existing one that's somewhere else, then it's just going to copy it over to the previous area. And then if you specified upload, then it's going to upload it. So these are the convenience functions that you can also get the element instance data from it, because this does involve a little bit of extra overhead because you are going to be storing a Lua copy of the instance buffer. And this is actually a little bit helpful. So it's a good thing to have this because you can get an element, change the values that you want inside of it, and then upload it back. You don't have to change all of the values inside of it, but you can do this, get it, and upload it back. So there are a couple of helper functions as well for primitives, for basic primitive functions. Like you can have circles. Now circles are very clever because you can use circles to draw both lines, a line circle, and a disk, if you call it in triangle fan mode. All you have to specify is the number of segments you want to split it to and the radius you want it. And it's going to give you a vertex buffer of a circle in the XY space. And it's also going to have a couple of extra bits of information. In the vertices, it's going to give you a circumference progress in one of the floats, and it's going to be, the radius is going to be constant. But the circumference is actually quite useful if you want to do some animation based on how far you are in the circle around it. It goes from 0 to 1. There's also a points. Points are simple. Points are just arbitrary pieces of data. And you can have X, Y, Z coordinates and whatever you want. This is trivially set up here. We also have a rectangle VBO. So this is a box, actually a 3D box with min and max X, Y, and Z, X and Y coordinates. And it also has, this is a rectangle. So this is for textured stuff. So it's going to have also U and V coordinates. So, you can UV map something. You can make a cone. Cones are sometimes useful. And you can also make boxes. For now, this is the primitives we have. I'm going to be adding cylinders and stuff, but it just makes a box. And the good thing is that once you have this, make this box vertex buffer object, it's a specific size, and you're going to get all of this information in the VBO data layout. Okay, so how do we actually use all of this? So let's take a look at the highlight geos. So with the highlight geos, there's a couple of, in these widgets, I always mark it with GL4, the stuff that's changed from the original implementation. That allows you to do a quick lookup of what actually changed. So we're going to need the Lua shader directory, which we use for the Lua shader. We are going to define a shader. We're going to define the instance VBO for now and the vertex array object. I don't think this is actually used at the moment because it's a member of the instance VBO table now, the vertex array object, so that everything is encapsulated. What do we have here? We have a vertex shader. Now I am going to go through this because there are some key pieces of information here. So this version indicator is required because we are using GL4. This line is going to be very helpful because this is going to tell the compiler, when you compile it, where to start calculating line offsets from if there are any errors. So if there's an error in this line, this is going to be an error in line 10,000. This is going to be an error in line 10,001. So have I talked about layouts yet? No, I haven't talked about layouts yet. So in this draw arrays instance fashion, you have a couple of layouts of data that your vertex shader and your fragment shader will also receive. So in this case, your vertex shader will receive in the location 0. Let me clone this to the other view. So in the location 0, what we're going to be receiving is the local position and alpha. So the local position and alpha, where are those from? The local position and alpha are in the, in this case, it's just the vertex buffer object, not the instance buffer object. So location 0, because it has an ID 0, there are up to 16 locations. This comes from the vertex buffer object. So that means that for every vertex of this vertex buffer object, which is actually very simple, it's just it's just 2 points in world space. So one is at Y position 1 and the other one is at Y position 1000. Why is that the way? Because it's 1000 Elmos high. It's very simple. So we're going to define this as this is what? Why is this 3? I don't even remember why this is 3. One moment. Well, never mind that. Oh, 3 is, in this case, it should actually only be 2 because that's the number of vertices that we have. So this actually should only be 2. And because we have 2 vertices, this is the vertex 1, this is vertex 2. For the vertex buffer, and we give it a name, which is optional, and we give it a size of how many floats it is. And note that it is now 4 floats in size, and I try to keep the name consistent so that you can tell the two apart. So this is going to be updated per vertex, and location 1 is from the instance buffer. Now what does location 1 in the instance buffer show us? In the instance buffer, when we called the make instance VBO table, one of the arguments was a layout. Now in this case, the layout is going to be, a layout is a table of tables. So each location has its own table entry. So for location 1, we have the ID 1. It has a name, which is optional, but I try to make it's the world position and scale. So that's going to be the world position of where we want to offset this individual array of lines. And yeah, and then we take all of the features. All right, and back to the shader. So what we have also is an out and an in directive in the vertex shader and the fragment shader. So the out is going to specify what values for the vertex shader will be copied into the fragment shader. And the good thing is that this will be interpolated across the graphical primitive. So if it's a line, this blended color is going to be interpolated from whatever value we set it to in one vertex to the other value in the fragment shader. You can also set these as flat if you wish, and then they'll be fixed for the entire primitive. So I also have this line here of engine uniform buffer definitions because it avoids well, copy paste and makes sure things that are consistent with the engine uniform buffers that we have. The engine uniform buffers are the ones that contain the screen view matrices, the shadow view matrices, everything from team color to the mouse position, and all kinds of very useful stuff. So this should always be done like this. Then what do we do in the fragment shader? Basically, all we do is we take the local position, the XYZ of the local position, and the XYZ of the world position, add those together, offset them. Then we also calculate a blended color. So we're going to, in this case, just make it yellow, because that's all we want to do. And the local position alpha, which is the fourth element in this XYZ and alpha value. Why is that? Because we have an alpha that's 1, so it's not transparent at the start, and it's fully transparent at the top vertex right here. And then in the fragment shader, we're not really doing anything. What we're doing is we're just doing this animation. This animation is just a fraction of the blended color alpha minus the time info.y. What was time info.y? Time info.y was game seconds passed. So what that results in is just basically this moving line right here. Very easy, quick animation. And then all we do is the fragment color is going to be the blended color that we get from that comes in from the vertex shader, and the alpha is going to be just this fractionally blended stuff multiplied by the previous alpha. So because we knew that we had the alpha from 0 to 1. Okay, so we compile this shader. Where do we compile it? In the make shaders function. So we take the engine uniform buffer definitions from the Lua shader and substitute them into both the vertex and the fragment shader, assign the vertex and the fragment shader to a Lua shader instance, give it a name, and then compile these. And if it doesn't compile, then we exit. Okay, so the actual use is then quite simple. The actual use in draw world is basically what do we do in draw world? Actually, that's not the usage yet. In the initialize, we take all of the geothermal vents and push an instance into our instance table. So this was the instance table that we created. And what we push into it is just the features X, Y, and Z position and a 0 because we're not using the fourth parameter. And I create just a string key for it to prevent duplicates. And because I know that actually some maps have duplicate geovents, I just realized this because that's why I had to add it, because some maps actually had geovents specified multiple times. And the true here means to update existing, meaning update existing in this function here meant that if we receive the same key, instead of giving us a message that we already tried to add that, this is a little bit verbose in the debugging for now. So, but it's helpful. I'm going to be removing the debugging once it's finalized and settled. So since we gave it an instance ID and we gave it the update existing true, means that we are going to update the existing element if it already exists. So we push this element, and then the drawing consists of, we're setting the line width to 20. We want a depth test because we don't want it to be drawn behind geometry. We activate the shader and then draw the arrays. Now the draw arrays, we give it the primitive type, which is in this case GL lines, the number of vertices that we wish to draw from the vertex buffer, the offset at which we start in the instance buffer, which is 0. We start at the the 0th instance because that's C based. And then this is the number of elements that we wish to copy, that we wish to draw from it. This is not the end index. This is just the number of elements that we wish to draw. And then I forget what the last one is, but you can also control, I forget what the last one is. Yes, that's a number of element that you've pushed so far into the instance table. That's you're going to be using the used elements quite a while, and it's the used elements is always that's maintained for you in these wrapper functions. So you don't have to worry about that. This is actually, I was very surprised on how easy it is to use these. So, and that's pretty much it. Then you deactivate the shader, reset the line widths to be nice, and you've drawn as many elements as you wish. Now, are there any questions on this part of it? Is there anything unclear about how it's used? Because then I'd like to go over a little bit more complex usage in the defense range version. Okay, so let's take a look at how the defense range one works. The defense range one uses the exact same thing. So the shaders there are much more complex. But let's take a look at how that one initializes itself. Where is the defense range? There's init gl4. So we have one vertex buffer for small circles for, I think, 128. Let me defense range. Let's copy this over to the other view. Yeah, that's so that you don't waste as much geometry. Not highlight geos. I want it to have defense ranges. Oh, I moved it to the other view instead of cloning it to the other view. Okay, here we go. Yes, exactly. So basically, since I'm using make circle VBO here, make circle VBO right here takes two arguments, circle segments. In this case, I think this is 128 and this is 1024. So this is 1000. And the radius is, well, if there's no radius specified, then it's a radius of 1. So that makes math so much easier later on. And then I'm making a new instance table for each class of defense range type, whether it's ally ground, ally nuke, enemy ground, enemy nuke, enemy air, because it's just easier to manage that way. This isn't final, but and it's not that wasteful, but it works reasonably well, and it makes managing what to draw much easier. So then that means we have actually 8 instance VBOs right here because of all the nukes and the grounds, and there's a different one for cannon, and I'll tell you why later on. There's a different one for cannon. So we initialize those. We make a vertex array object and attach both the small and the large circle to the vertex array objects. These are the instance buffers in this case. It's a table of instance buffers. I know that sounds nasty, but it works pretty well. It's a table of instance tables. And we initialize those, and what else do we initialize? We initialize GL4, and that's pretty much it. And then we make the shaders. Now the shaders in this case, I'll actually go through there's a little bit more complexity involved in the layouts and what kind of items are present in the shaders. Now, since we have our circle vertex buffer object, the layout of that is trivial. It just has one vec4, which is the position that we've discussed. It's a circle in XY plane. For the cannon shader and the non-cannon shader, we have two different sets of shaders. The vertex shader is different for them, and I think the fragment shader is almost the same. So we also use, in this case, a couple of uniforms. Now the uniforms that we're using are going to be the height map texture and the LOS texture, the line of sight texture. So these are in just increasing order. And we're also using uniform floats as an example. I don't think I actually have to set them because everything else is done in the shader. Then I give them just, a name, and the layouts themselves are the ones that are very important. And the layouts are, where are the layouts? Is, hey, welcome. So the layouts are right here.
So can I add something?
Yes, sure.
Yeah, you can actually skip this uniform int and height map text and loss text and define these numbers right in the shader.
Oh, so those are part of the buffers now as well, the uniforms right here, the engine uniforms?
You can specify it. No, not here. But can you show me your shader code?
Yes. Let's go into the vertex shader code. It's right where the uniform samplers.
Yes.
It's these,
Somewhere on top.
right here.
Yeah, you can specify here the actual binding index, binding slot. I'll send you the syntax later.
Okay. Excellent.
Yeah, go on.
Okay, so the instance VBO layout is a little bit different this time. Our vertex VBO only had the vertex position, which was the circle point position. But we're adding much more information per instance of circle right here. We're adding a position and scale, which is going to be the XYZ position and the radius of the circle. We want a color, which is just going to be a vec4 of color. We want a visibility. We can pass in a visibility as a height draw start, height draw end, fade factor in, fade factor out, and a couple of projectile parameters. This is for doing the sampling of the height map and identifying whether a cannon can fire there or not. So this is just engine parameters. We have these mirrored right here in the vertex shader. We have this comes from the individual vertices, and this comes from each instance ID. So this is going to be identical for each instance ID. So we don't use any uniforms yet. What we are using is the height map texture and the line of sight texture. And then what we're going to output from this shader into the fragment shader is a world position, a blended color, some alpha control parameters, and that's pretty much it. So the math here is there's some useful functions here. We can get height at world position, which is we get the actual height and Elmos by sampling the height map texture based on the world position coordinates right here, and it's done to be safe. And then there's a lot of nasty math here of trying to replicate how the engine calculates range. So I'm not going to go too deep into that because if anyone wants to, they can read it. And then we pass these into the fragment shader, where we only use, in the fragment shader, we have the data coming in from the vertex shader, which is the world position, blended color, alpha control, and we blend these all together in hopefully a nice fashion. Now, how does the setup actually work? The setup works in a way where where's the push element instance? So I want push element instance, which is whenever we identify that we have seen a new unit that requires a defense range ring, then we push it into the correct buffer. We make a new key for it. And the data that's pushed in is the XYZ position, the range, the color, fade start, fade end, and oh wow, this is actually wrong. Very good. Nice catch here. And the weapon parameters that are pushed in. So whenever we have a new one, whenever one dies, we can just, we store the keys that we used, so then we just pop the elements if the unit was destroyed. There's one pop here, and there's one pop here. That's one's for mobile NTs and one's for static defenses. Static defenses are managed differently, but with this one, if the mobile NT unit gets destroyed, then that gets pushed in. So they are also updated in a different fashion. So mobile NTs, whenever they are seen, they are updated using push elements instance. If you use the same key and set update existing to true, you can update them. How do they look? Well, we can start by Alt cheat. Let's give it a RMLT, and we see that it has a beautifully nice perfect circle of range, in this case, which seems to be wrong. Why is it wrong? That's novel. I think I screwed something up. This should be perfect in range, but it's not. Odd. The cannons are, though. So what else you can see from this shader is it does things like you can see these circles fade in and out when you put the mouse nearer to them, and all kinds of clever stuff. Like if the mouse is away, then it doesn't show. And this shows the actual cannon range, and it's actually more accurate than the one that's shown by the engine, because if I fire here, then the cannon won't be able to fire that far. Yeah. So that's pretty much it. Do you have any questions on the implementation details? Excellent, excellent. So the main cost that you should be thinking of is updating the buffers is what's expensive. So if you're going to update a lot of them at once, then you might want to, every frame, that might not be efficient. So you might want to think of simple workarounds, like in the in the example of radar ranges, so slash give 20 arm peep, we see that the circles drawn by this are, yeah, they should be overlapping. Well, they're done with the stencil buffer, so they kind of overlap, but they are updated every frame. You can see that. But they're faked. They're only updated every 15 game frames, and the shader is actually interpolating between them in the start position and end position for every 15 frame because it has every other piece of information that it needs. So this is for the radar ranges, and it works surprisingly well for things that don't need to be updated fast. It's actually way better than doing it 15 times. I mean, 15 times is more frequently. So whenever I push into this one, I push when a unit is created, and then I push on every 15th game frame. Now, there is some nastiness involved here because it turns out that taking all the units, getting all their instance data is right, where was that? In the instance VBO table. So whenever I get the data for a instance, it's creating a table. Where was the getter function? This is to make the layouts. Yes, get element instance data. This is going to return the table of that instance data. And getting this and pushing it back is more expensive than directly manipulating the buffer. And then after that, the Lua side copy, and then after that, uploading everything in one go. So this is a little bit more efficient. Yeah, edit the Lua side copy and then uploading it all. I know this isn't as nice, but if you have to update the entire thing, then it's much faster than getting the elements, with getting a table of it and then pushing that table back in. And you get the advantage of practically zero load. So I can give, I don't know, 200 arm peeps. Yeah, well, not peeps, 200 arm peep. Set them on patrol. You can see their radar range, and I go F into the widget profiler. Let's take a look at radar range GL4. Where's that one? I'm not sure I can find it. Radar range GL4, less than 0.1% load. Okay, 0.20%. So nothing. Then this is for drawing 200, and they're updating them every 15 game frames. And it's, the old one was about 20%. I can show you the old one. The old one was radar range. That's the old one. So the old one is using, for 200 peepers, it's using 30%. So the difference is indeed huge. So it's very worth doing. And same with defense ranges. The defense ranges are actually very similar. So if I have slash give, I don't know, 200 arm LLTs, then for F11, I can turn on the old defense range as well. I'm going to self-destruct the peepers to make it a little bit more fair. And with defense range, we have the old version is about 3% load, and the new one is 0.1%. So practically costs zero. And you also have these nice effects that yeah, right now they're overdrawing each other, but yeah, they're much more useful. It actually looks better when it's not as as frequent. So let's say you have just a couple of LLTs strewn about, and so I go F11. Let's disable the widget profiler because it's hiding everything. So I zoom out, it's invisible, and you zoom in, and they highlight back in. This needs a bit of tweaking, but we'll get there. So same with those small LLTs outside. If we zoom in, it'll show up. Well, obviously, no one uses defense ranges on allied stuff. It looks weird. But for enemy stuff, it works perfectly as well. Okay. Are there any other questions that I can answer? Okay, the two things to take in mind is if you want to take a look at the underlying implementation of what the exact parameters are, then they are Lua VBO implementation and Lua VAO implementation.cpp. These are the two files in the engine that you can take a look at, and pretty much I also have the GL4 table, which contains links to gists of code. Whichever one I completed, it contains a link to the gist, and there are examples of ones using geometry shaders. So Snow is using a geometry shader, which is very nice. And what else? The rest of them don't use geometry shaders. But yeah. Did this somehow get edited? There's stuff missing from this. Oh, an importance. Yeah. Oh, it's completely fine. Oh, it's completely fine as long as it didn't screw up the ordering, so it's probably going to be fine. Yeah, Flow UI and Chili are two difficult ones. Like the ones that I'm going to be tackling next are most likely going to be health bars, because that's going to need a geometry shader for being good. But like doing metal spots is a good idea. Doing the ones for custom formations is very good. Using the smart selected units, the fancy selected units, commands FX. These are all ones that are very good to do. And I don't know if Ivan D's still here, but I've been thinking a lot about how we need to replicate this kind of function by being able to do it with the draw function at unit thing. So you want to draw an instance at a unit. Like when you want to draw all of the selections for a unit, you don't want to update the position of the unit every frame. You don't want to update the buffer, so it might be better to have those exposed towards from the engine side in these uniform buffers, because we already have a lot of good things exposed. So even just getting team color.
Yeah, the way you do it is that you actually pass one integer
Mm-hmm.
as an SSBO offset,
Mm-hmm.
and this offset will point out to the big GPU array that contains all kind of matrices, model matrices, pieces matrices, static pieces matrices,
Mm-hmm.
etc. So, so by specifying this offset, you will be able to actually track down a specific unit or feature or piece or whatever you like,
Mm-hmm.
actually. And similarly, how you have your this uniform params buffer and uniform whatever matrices buffer, you have actually reference to this GPU buffer containing all matrices. And from these matrices, you will be able to get position, rotation.
Oh, that's
Uh,
excellent.
yeah,
Because one of them.
it works at the moment. It's not ideal, I would say, in a way that the offset is not guaranteed to persist between the frames.
Mm-hmm.
So if your units are getting created and die, the offset changes. But I actually almost implemented the proper, let's say, implementation such that the offset stays same in the inside the game, basically.
Excellent.
So if you have offset of 100, it will stay 100 until your unit dies.
Can the offset be the unit ID?
Um, not quite. I tried this approach. It required some smart, let's say, hashing.
Okay.
So you hash unit ID into some range, and you obviously have to deal with collisions and nasty stuff. Kind of worked, but I think I hit some unresolvable issues, so I scrapped this idea. So what you do instead is you gather the offset via Lua API,
Mm-hmm.
exists nowadays. So you gather this offset. Right now it's not stable, so you have to kind of update it every now and then, every draw frame potentially, or every sync frame potentially. But moving on, you will be using the same API.
Mm-hmm.
You will be gathering this offset. You will be putting it into the instance buffer, and from the instance buffer, you can basically take this offset, uh, read the matrix at the offset, whether it will be kind of unit position, matrix number 0, or piece number 0, piece number 1. You just increment this offset by 0, 1, 2, 3, 4, 5, and you get the right matrix.
Perfect. That's going to be
Yeah,
excellent.
yeah.
Okay. Um, okay, Master Bell, did it answer all your questions? Okay. Okay, thanks. I think I'll stop the stream then. And excellent.